Really happy to be here. Actually, a bit about me, for those who don't know. I'm a self-taught JavaScript developer. So I worked at Google and also an open source JavaScript company called Meteor. Anyone have heard or used Meteor in the past? Whew, OK. So I've been an independent open source developer since 2016 and worked on a bunch of projects. You probably have heard about Vue.js or Vite. Any of you have heard or used it? OK, great. So I founded a company called VoidZero a while ago. So we're building a unified tool chain on top of a bunch of open source that we built. VoidZero maintains open source projects, including Vite, the build tool, VTest, the test runner, wrote down the bundler, OXC, which is a low-level compiler toolchain, including linter and formatter written in Rust. Putting all of these things together, we announced a thing called V Plus just this past week. So Google it and check it out. But I'm not here to pitch the thing. I'm here to talk about build tools. And why are we building build tools? How do we make them faster? And the challenges. Because we've been dealing with these specific challenges when trying to build faster tooling for JavaScript developers. Right? So this is a bit more focused on front-end tooling. Right? So we're talking about people building really, really large front-end applications. Right? But let's take a step back. Why does JavaScript need build tools in the first place? Right? In the old days, it was really nice to just pull in jQuery, and you're good to go. Right? No build step. There are a very vocal group of people who want no build step, even today. Unfortunately, right, it's because we are building different kind of things on the web. Right? We're building more and more ambitious, some insane scale applications in the browser. Right? And also, JavaScript as a language was designing 10 days, wasn't really set up for the task to deal with the scale that we are throwing it at today. Right? This is not Brandon's fault. It's simply because, right, it's just over time, we ran into these problems that the language wasn't, the author just didn't anticipate, right? So we have these files getting too large, and all of them share a global scope. What do? We need a module system, right? And how do we share this code we just wrote with other people, right? How do they install it? How do they manage it? We need a registry. We need a package manager, right? You can't just ship thousands of modules directly, thousands of network requests directly to the browser. That'll be too slow. We need to bundle the things, right? New language syntax come out, right? ES 2015. We want to use it now, but browsers don't support it yet. Let's transform it. Let's just build our own compiler, right? Files too large, you need to minify them. Making sure it works, you need test runners, linters, type checkers, formatters, right? And monorepos. They get crazy, right? Now we need to think about how do we orchestrate the tasks so they can run in parallel? How do we cache them when things didn't change? Right? All these problems emerged at scale, and there was nothing about it in the language itself when it first came out. So what do we do as JavaScript developers? Well, thanks to Node.js, we were able to write our own tools, right? So we wrote our own tools with JavaScript. So you are probably all familiar with the tools listed here, right? All the way from parsers to bundlers to test runners. The common thing here is they're all written in JavaScript for JavaScript. And it was great, right? JavaScript developers solving our own problems. We actually managed to turn it into a language with proper engineering best practices. Now we have a whole suite of tools that we can pull from NPM, right? Despite Node modules being really heavy, it kind of worked, right? And we were OK with dealing with some churn, dealing with some inconsistencies. And yeah, so we were able to build crazy things on the web, right? Things like Notion, things like Linear, right? Products, really polished, long-running application with rich interactions on the web. That's the power of the web. That's the power of JavaScript. And thanks to these tools that we made. But over the past 5 years also, right, these JavaScript tools written in JS started running into performance bottlenecks. We started to see, just waiting for minutes to start a dev server, right? Waiting for like 20 seconds when you save a file just to things update in your dev server. Right? We're waiting for minutes for the link process to run on our CI servers. And that just elongates the feedback loop. It makes catching bugs more difficult. You're reluctant to run these things locally. You're reluctant to run your tests. You're reluctant to even start your dev server, right? When you hit save, you go and take a cup of coffee, right? Not fun. And how do we make them fast, right? We started building faster tools. And starting 5 years ago, there's this new crop of tools for JavaScript written in native languages, right? SWC, OXC, Biome, all written in Rust. ESBuild is written in Go. TurboPack, Rowdown, TurboRepo, NX, JSR, Volt all have Rust components. TS is being written in Go. And of course, there's Bun, which is written in Zig, right? So how much faster are these native tools, right? You better have a good reason to reinvent the wheels, right? Turns out they are really, really fast, right? So these are the numbers when we compare Rust equivalents or native equivalents to the PrevGen JS tools, right? These numbers have ranges because it depends on the workload. In fact, the advantages gets bigger and bigger when you throw even larger workloads at these tools, and also when you have more beefier machines with more cores for parallelization, because native tools are just better at leveraging those cores. So it's great that we are getting this kind of performance bumps. Some of you probably already benefit from these, right? In fact, a lot of these native tools are already quite popular in people's build stacks. But we didn't get here for free, right? In the process of us working on things like OXC and Rowdown and trying to get those things into Vite itself to make Vite even faster, right? We had our fair shares of challenges and learning. So here I'm here to kind of share that, some of the things we've witnessed and some of the things that's probably commonly shared across all these native tools that's currently being written or worked on. So the challenges and trade-offs, right? First thing we kind of want to get out of the way is the language choice, right? Notice there are 3 main choices here. There's Rust, there's Go, there's Zig. The thing with Rust is it probably has the most robust sort of type checking dev ecosystem, and in terms of having the balance of being a strict language, memory safety, but still allowing you to be productive, right? The thing is, all these languages requires careful memory optimizations to make sure things are fast. So we'll talk a bit about some of those specific things, right? And specifically in Rust, the ownership. Any of you here write Rust? Have you struggled with life cycles, ownerships? So it can make certain code really hard to write, right? This is one of the reasons when the TypeScript team thought about porting TypeScript to a native language. They look at Rust, and it just turns out some of the dynamic nature, the code patterns in TypeScript compiler that enabled by the dynamic nature of JavaScript isn't that straightforward to port over to Rust, right? On the other hand, Go actually gives you a much more sort of directly comparable mental model where you can sort of just mutate things, and garbage collector will do its thing. However, garbage collector turns out to be quite challenging when you have extremely large workloads. And this is exactly the problem we're seeing in CSGO right now, because we are building type-aware linting on top of CSGO, and we're running that in some of our partner companies' extremely large code bases. And sometimes it can be even slower. The garbage collection is actually a major bottleneck when you have huge monorepos in TS Go right now. Obviously, we trust the TS team will figure things out and improve it, but these are real problems we're seeing, right? And also the WebAssembly story of Go is kind of not so great compared to Rust. And an important consideration for us when we build web tooling is we often want our tools to be able to run in the browser, right? For example, Rowdown ships the whole OXC toolchain, and Rowdown can be compiled to WebAssembly and run directly in your browser, so you have a very snappy, instant playground where you can do things, or it can run on platforms like StackBlitz, which enables you to spin up a whole app dev environment in your browser really quickly. And finally, there's Zig. Honestly, I don't write Zig, but from what I heard, you need to be really, really cracked to ensure memory safety, and it's kind of challenging, right? So you need someone like Jared to be really handle this in the long run. For us, it's just easier to trust Rust and hire people who like Rust. OK, so even with native, performance is not guaranteed, right? Like I said, efficient memory management is really important. Specifically in OXC, one major difference that differentiates OXC from SWC is we use arena allocators. Essentially, it means we put the AST in a consecutive chunk of memory, and so that we can drop the memory when this thing is done in one go, instead of a fragmented memory management, right? And turns out this really helps with performance. It also unlocks some interesting things that we'll talk about later, right? We put a lot of effort into optimizing memory size as memory consumption as well, right? We try our best to use really compact AST data structures. And we also do things like preemptive allocation for semantic analysis, which is constructing the scope structure in the AST, which can be quite expensive. So again, memory management really pays dividends here. There's also requirement for keeping good architecture design. Actually, it becomes even more important because now you can leverage more cores. How do you maximize that capability, right? So an example is ESBuild. So in a bundler, typically you have to go through parsing all the modules, generating the ASTs, analyzing the relationship between them, link them into the module graph, and finally generating the code. Turns out the parsing phase and code gen phase can be entirely parallelized across all the modules, but the linking stage cannot. So you have to carefully design around these constraints so you can do as much work as possible in parallelization. And in fact, ESBuild's architecture inspires the architecture of what we use in Rowdown. It inspires what Buns Bundler is built on top of. In fact, Buns Bundler is largely a Zig port of ESBuild. So thanks ESBuild for paving the way here. And there are more areas that are eligible for optimizations when you go native, right? Things you don't even think about when you're using JavaScript. Operating system specific and even syscall level optimizations. A good example of this is Buns Package Manager. Why is it so fast? Because it goes native and it optimizes even at the syscall level. It just invokes an order of magnitude fewer system calls compared to a package manager that's written in JS. And right, that results in huge differences. So, but this is also very, very difficult for you to you need to just put a lot more energy because you don't even need to think about this kind of problems when you're writing JavaScript. So how can we keep things, so other challenges as we keep going. How can we keep things fast while cramming in more features, right? There are, when you build an end-to-end build tool, right, ESBuild contains multiple features like transformation, transforming TypeScript, transforming JSX, transforming syntax lowering to ES 2015, minification, tree shaking, dead code elimination, all these crazy things. It actually combines all these different jobs into maximum 3 AST passes, right? So there are some trade-offs here because when you sort of mix the concerns in 3 AST passes, you're sacrificing some layer of separation. You're sacrificing some maintainability in order to get the best possible performance. And there are some similar things we do in OXC as well, right? So in OXC, we do separate things like transform, parsing, and minification. But in the transforms, we actually apply all the transforms in one AST pass using some custom traversal logic that we've come up with, while also playing nice with Rust's ownership model. So that took a lot of work. There's also the speed versus depth of optimization problem, right? So when you ship JavaScript code at massive scale, sometimes applications shipping megabytes and megabytes of JavaScript, you want to be able to split them nicely. You want to be able to ship as little code as possible. You also want to ensure good runtime performance. So there are a lot of things you can do at the compiler level to ensure those, right? I think Meta actually did something like pre-pack in the past to explore this, right? So there are like constant evaluation, tree shaking, DCE, minification passes. You can actually do multiple passes. There's also complicated chunk splitting algorithms. And you need to cram all these things in, additionally, to the bundler. Again, you need to keep things fast. Like, you can't just go infinitely deep on, say, constant evaluation, right? That comes at a cost, and you need to find a good balance to stop and ship the good default balance to your users. And finally, this is probably the most important thing that we've run into when we're building our tools, is speed versus customizability, right? Because when we shipped Rowdown, the very first version, and we use it to bundle a thing and compare it to rollup. We're like, wow, we're 30 times faster, crazy, awesome. But then our user comes in and they're like, do you support JavaScript plugins? Because I have tons of rollup plugins I want to use with Rowdown. So then we tried it, and turns out the performance gains you just get demolished. You just it's crazy because turns out JavaScript developers likes writing JavaScript plugins in JavaScript. So there are many examples of this, right? When you use ESLint, there are custom ESLint plugins rules. Guess how many ESLint plugins are there on NPM? Anyone take a guess?
10,000.
More than that. 280,000? Yeah, that's how many ESLint plugins are there. Some of them may be AI generated, I don't know. But there are also custom transforms, right? How many of you have written a custom Babel transform? Quite a few of you, right? Like React compiler is still based on Babel, and that makes us sad because we have a vanilla Rowdown Vite application running React, and it's blazing fast, and the moment people add React compiler, it becomes 8 times slower, and like, oh God, we wish we can port that to OXC, right? The door is open. Yeah. There is also like many legacy CSS in JS solutions. I blame Christopher for that. And then there's like frameworks, right? Like Solid.js, Vue, Svelte. We all have some part of our transform pipeline that's still in JavaScript, right? Vue and Svelte actually uses something called magic string, which I'll also talk a bit about later. So there are many examples of these, right? When we think about, OK, we built this great Rust bundler that you can use, and the user just adds tons of JavaScript plugin on top of it, and we're back to ground zero. So what do we do about it, right? It just tanks perf. So what do you do? Maybe that's a solution? Well, joking, right? So specifically in OXC and Rowdown, we've tried to come up with some ways to mitigate this, right? So in principle, we want to invoke fewer JS calls from Rust, because that's actually expensive. We want to make passing data from Rust to JS cheaper. We want to avoid having to pass stuff from JS back to Rust, and just do more work on the Rust side while keeping a similar API. Okay? It's not going to be perfect, but there are things we have did and things we're planning to do that hopefully will improve the situation. So this is a typical Vite rollup plugin. Right? If you've never written one, just focus on the logic here. There's a transform hook. Inside the transform hook, you're doing a check. Right? This is the custom CSS transform. So you check if the file ends is actually a CSS file. And if it does, then you do some transform. Okay? In a pure JavaScript system like rollup, this is totally fine because the check is actually quite cheap. However, in a Rust-based system, you're actually going all the way from Rust to JS just to invoke a very cheap piece of check logic, right? When this whole work can potentially be skipped if the file is not CSS to begin with. So what we can do is, so just to illustrate how expensive this is a benchmark by adding multiple copies of this plugin and just compare it to with no plugins at all. So when you add 10 plugins like this, the whole build becomes 3.7 times slower. Okay? So one thing we did is we just add this thing called filters. This is actually also another idea that's pioneered by ESBuild. ESBuild just did this from the get-go because it knows the problem exists. Right? We're coming from a different perspective because we are trying to be compatible with an existing plugin ecosystem. So this is like solutions to help them migrate over to a more performant, best practice. When you add the filter, the check logic now is moved to the Rust side. So we can do the check on the Rust side without leaving Rust and just stay in Rust land if the check fails. Right? So with this, as you can see, with 10 plugins, we are only paying a single-digit percentage performance cost for these plugins now. So this makes things much more manageable and scalable. Another aspect of it is sending AST from Rust to JS is slow. There are many plugins, like I said, where inside the Rust system, a custom transform plugin can still do the parsing in JavaScript, right? We already have a Rust parser, but we're just sending a big chunk of string to a JavaScript plugin, and the JavaScript plugin parses again with JavaScript. So how can we get rid of that? The idea is, OK, let's parse it on Rust side and send the AST over. Turns out that's also really slow because you are copying the memory from Rust to JS, and that's not cheap, right? So OXC raw is like 19 times faster than Babel at parsing, but once you're adding the transfer cost, it gets 14 times slower. So one thing we did is something we call raw transfer. Turns out because we use an arena allocator, the AST is already in the consecutive chunk of memory. So we just send the whole thing over to a shared array buffer, and then let JS reconstruct the AST on the JS side. So at least we avoid the memory copy. Turns out that's slightly faster, but not as good as we hoped. The reason is that we're constructing too many JavaScript objects for huge ASTs. And when we think about the use case, say when we're building a linter, turns out most JavaScript linked rules don't need to visit the full AST, right? It's interested in specific AST patterns. So for example, it only cares about a const destructor, a destructor pattern inside a function signature, things like that, right? So we want to construct easy ways for you to specify that logic on the Rust side. So we can do that check on the Rust side and send only a subset, either send only a subset of the AST over, or we can do something called lazy deserialization, where we only construct the JavaScript AST objects for the nodes that you actually care about, right? So the example here is if, say, the node debugger ESLint rule, it only cares about debugger statements. If we narrow it down to that, we can get lazy and adding lazy deserialization. Now we're back down to maybe 2 times of the cost of a raw AST parse on the Rust side. So that's actually quite decent. And this is the foundation of shipping ESLint compatible custom rules and plugin support in OXLint, which is our Rust-based linter. So in Rowdown, we're also doing similar things, right? So when we tackled the AST raw transfer and lazy deserialization, we realized, OK, transform hooks can use this too, right? So if you want to write a custom transform, right now, I don't know how many of you have used magic string, but the idea is you get an AST first, you traverse it, and figure out the nodes you're interested in, get their AST, the locations, and then you just say like append some strings next to it, or just move it around. You can call these manipulations, and eventually you generate the new string and you get a source map. So very straightforward, actually quite useful because like the whole rollup architecture, the whole Svelte compiler, Vue compiler, they're all written using this, right? So how can we move this whole ecosystem to make it faster? This is how it does it today. You get the code string from Rust. You're still parsing the whole thing in JavaScript, traverse the whole thing in JavaScript, call the methods, generate the string source mapping in JavaScript. You're doing tons of work in JavaScript and then send the whole thing back to Rust. How can that be fast? It can't. It's slow, right? So this is how we want to solve it. The transform hook gets the raw AST from Rust. You lazy traverse the AST, only visiting the nodes you're interested in. You call the magic string methods. It's the same transform logic. You can actually keep most of the logic, except you don't do any extra work on the JS side anymore. We just send these calls back to Rust and let the Rust handle the string and source map generation, right? So that'll be orders of magnitude faster. And this is something we're shipping in Rowdown very soon. So talk through a bunch of things. This could be a really dry talk compared to Sarah's, but the goal here is let's make fast native tools without leaving JS plugins behind, because JS developers need to be in control of their tools, but we also want them to be fast. So this is what we're working towards at VoidZero. So if you're interested in what we're working on, check it out at voidzero.dev. Thank you.